Hi, my name is Sean Branchaw.
And I'm Abasiama Akpan. Our topic today is the relationship between the snowshoe hare and the lynx, which is the Holland Type 2 model. Our abstract is relationships in nature between predators and prey can often be described with mathematical models. These models can reveal interesting observations about defining characteristics of the predation occurring and can lead to further knowledge of the relationships at hand. We'll be specifically looking at the Holland Type 2 model to describe the relationship between the lynx and the snowshoe hare. We will both solve our model and look at bifurcation plots and phase portraits describing our model and show what happens as various outside circumstances occur to the environment.
Before we get started, we have to talk about some of the assumptions we're making in order for this model to work. The first assumption that we make is that the lynx diet consists entirely of hares. Now, this isn't exactly accurate because it can consist anywhere from 50 to 99% of the diet, but we're choosing to say that it consists entirely of hares in order to make the model work. The second assumption we have to make is that the birth rate is actually a constant. Now, in real life, the birth rate varies with the population of the hares, with the various season climate changes, but we have to assume that it's a constant, and so we did that through the use of weighted averages. The third assumption we have to make is that the mortality remains constant. Again, this is similar to the birth rate constant, and we tried to find it using weighted averages, but if we were doing a more accurate model, we could try to use that, represent that via variables. Another assumption we had to make is that the carrying capacity for the hares is 2 million hares. Now, we based this off of data we had found, but there's nothing that says for sure what the carrying capacity is, so that had to be an assumption as well. The last assumption we had to make is that no predators prey upon the lynx. In real life, there are actually several predators that prey upon the lynx, but it's very unoften in occurrence, and so it wasn't worth adding into the model. Again, if we were trying to make this model even more accurate, we could represent that with some sort of harvesting variable. This is our prey equation, and this is our predator equation. It's got quite a few variables, so I'm just going to go through and explain what they mean. The x of t denotes prey, and the y of t denotes predator. R and S are the intrinsic growth rates. K is the carrying capacity of the prey, which is proportional to the size of the prey, so it's actually directly related to the x variable. H is the prey-dependent carrying capacity for the predator. Mx over A plus x, the whole quantity multiplied by y, is the rate at which predators remove the prey. That's the Holling-Tanner type 2 response. That's what makes this different than the Holling-Tanner type 1. And then M is the max number of prey that can be eaten per predator per time, and our time is going to be a year. A is the saturation value, which corresponds to the number of prey necessary to achieve half the max rate of M. At this point, we're in a good place, but unfortunately, all our variables and constants and everything have dimensions, and we would like to remove those dimensions because the model is able to be much more useful and much more broadly used if it has no dimensions. So we're going to re-index these and remove all the dimensions, and here's the process by which we do that.
This is the prey equation. By plugging in y bar, we didn't have a specific variable for y, so we used the symbol y equals this, and we solve for y, and we go y bar rx over m. dt, this is x bar, and we solve for x, and this is dt bar, and we solve for dt. Here we plugged in dt, and by simplifying, we got this equation. We plugged in x and y bar in this equation. Then we simplified and got this equation. And due to the process of reindexing, we are allowed to absorb the k's, so we get this. And then we drop the bars for simplicity's sake, and we get the reindexed equation.
Here we have the predator equation with the t-bar plugged in. Again, when we plug that in and do some simplification, we will cancel out, and so we get this. We then plug in our values for y and x again, and we get this equation. We do some more simplification, we get this. And then we do some manipulation, and we set rk over m to delta, and we set hr over m to beta, and we get this equation, which is much nicer looking. Then dropping the bars again for simplicity's sake, we end up with this final predator re-indexed equation.
Now we have the first two equations, and we're going to solve for them and look at the graphs. We have the tools we need. We're also going to plug in alpha, beta, and delta. We're going back to what we defined the predator and prey equations to be, and this is what we found. We derived the equations from the data we already researched. Even though these are in the form of decimal, they actually represent large numbers, the initial conditions right here. Alpha represents 10,000 and beta represents 1,000. For the sake of scaling, we've made the initial conditions decimals. The initial conditions represent our starting population for each animal, which is the lynx and the snowshoe hare. X naught and Y naught represent the total amount of animals living at the moment. We make our step size small to get a very good curve, and here are the plots.
Here's our first plot. It's representing the cycle of the populations of the animals, and you'll notice that as the blue is going down, it corresponds with a red going down, but they're not exactly aligned, because as the hares are starting to die off, a delayed effect happens, and then the lynx starts to die off. And again, when the hares start to rise in population again, it takes the lynx a little bit to catch up, but they start increasing again too. And what you'll notice on this, and we'll see as we increase the time, is that these actually start stabilizing. And eventually, given enough time, it looks like they would actually stabilize to an exact value somewhere along the point. Now, that's not necessarily completely accurate according to a realistic sense, but as the cycle continues, it would become less and less severe, as this graph shows. Here's our second plot, and this one's very interesting. It's the face portrait, and you'll see that as time goes on, again, it's stabilizing, and it's interesting because as time goes on, you watch it as the prey increases, the predator increases, and then the prey starts to decrease, which causes a decrease in predator, and so on and so forth, and it goes in and in and in and in, and eventually it just starts going towards this stabilization point that we were seeing in our first graph. And it's looking like it'll stabilize somewhere around y equals 0.25 and x equals 0.07 or so, which would correspond to some larger numbers, as Abasiama was talking about earlier. Our third graph is a slope field or direction field of what this would look like with various initial conditions. And as you can see, it follows the same formula as it goes. It becomes a bigger type of circle, or it's more of a squished circle, but it just becomes bigger and bigger as the initial conditions change, which is pretty interesting. We now want to take a look at a case study of what would happen if we started messing around with the initial conditions, which is essentially talking about what would happen. In this case, we're going to see what happens if the lynx population happened to go extinct. So we go ahead and plug in 0 for our initial condition for y, which represents the lynx population. We go ahead and enter that in, and we go through, and when we look at the graph, it's pretty interesting because you see here the lynx population is completely dead, but the hare population explodes. And in just a matter of a few years, it goes to its absolute maximum. And then this model starts failing to predict what's happening because there's no harvesting factor and there's nothing removing the hairs, so it becomes more unrealistic. But you can see that it is realistic that as soon as the lynx population was gone, the hares would exponentially increase, and eventually they would end up stabilizing at some huge high point. Another interesting case occurs if we set the hare population to an enormous number. We're going to say 1, which in this case represents a huge number. Now, this would represent in real life probably trying to shock the environment with thousands upon thousands of hares in order to maybe increase the lynx population to prevent it from going to extinction. So we see what happens here. We plug these in, and when we look at the graph, something very interesting happens. You can see that it starts out initially with a very, very high hare population, but almost immediately, within a few years, it goes right back to where it was on our initial graph with just a smaller hare population. And again, they start stabilizing at their original places. So it didn't help the lynx at all, which is very revealing. In summary, you can see that no matter how many hares you were to infuse into this situation, they're always going to want to tend towards this equilibrium point. As if you mess with the number of lynx, you get similar results. It always wants to stabilize towards the equilibrium points. And it doesn't really change based on the initial conditions, which makes sense because in a real life circumstance, anytime you were to pinpoint a specific time, you would have differing initial conditions based on what stage of life they're in. It could either be a high point of hares, or it could be a low point of hares, it could be a high point of lynxes or a low point of lynxes, but it's all part of that model that's very cyclical, and it's always going to stabilize towards some point. This has several implications to real life that make this very interesting to study.
To make this model more precise, we could add more prey, such as for the lynx, such as squirrels and rats, which we could also add predators for the lynx, such as lions, and introduce variables for the birth and death rates rather than constants. The model also is helpful for conservationists and environmentalists as they study species of lynx that are endangered. It can help them show the years and seasons extinctions of lynx is highly possible. This will help them prepare beforehand in building habitats for these animals. The model is relevant to predicting extinction of both the lynx and any other interaction. It will still yield the same result if evaluated. And remember to pray for your rabbit.